Okay, and the next presentation, anisotropy of hydrogen embrittlement of ferrite-pearlitic steel considering operational degradation. In this talk, I'd like to concentrate on influence of long-term operation on anisotropic mechanical behavior of pipeline steels. It's a very important research question in the problem of safety and reliability of using existing natural gas pipelines for hydrogen transportation, or it's a mixture with natural gas. So here there is a presentation outline. At the beginning, I'll give you a short introduction about the problem of hydrogen-assisted degradation of pipeline steels and also sensitivity of mechanical properties of steels to degradation. And then we'll consider some peculiarities of influence of long-term operation on anisotropy of strength, plasticity, and hydrogen embrittlement of pipeline steels. And finally, some concluding remarks. It's well known that green hydrogen currently plays an important role as a decarbonized energy carrier, and it's already widely used in various industries. However, its widespread usage in global energy transitions faces some challenges, including influence of hydrogen on mechanical behavior of materials used for hydrogen transportation. And hydrogen can be transported cost-effectively by pipelines, and here you can see some data presented hydrogen transportation pipelines safely operated in their Northern Europe and also in the USA for many years. However, there is no sufficiently development national hydrogen networks, and their construction will take significant time and require sizable investments. Therefore, it's advisable to consider using of existing gas transit pipelines for hydrogen transportation. And as you know, Ukraine has the extended network of gas pipelines, and they haven't been used currently at full capacity due to a significant reduction in gas transit, and also future process of decarbonization will only force this situation. And as you know, recently, a European Commission presented a new plan to rapidly reduce dependence on Russian fossil fuels. Ukraine has joined European Hydrogen Backbone Initiative to have operating a hydrogen network in Europe by 2040. There is a great prospects for Ukrainian natural gas pipelines, especially taking into account current situation in the western region of Ukraine for hydrogen transportation. However, such a prospect for repurposing gas natural pipelines for hydrogen transportation can increase risk in its structural integrity loss, and the most important factors are in-service degradation of pipeline steels and also potentially harmful influence of hydrogen on mechanical behavior of materials. So a significant part of gas pipelines is operated near the end of their design life, and here we can see that two main stages of in-service degradation of pipeline steels were distinguished. The first stage is deformation aging, and the second one is damage accumulation. And the important role in the second one plays hydrogen charging of pipeline steels under operation. And as you know, the main problems of in-service degradation are embrittlement and also deterioration of mechanical and corrosion properties. So here you can see how hydrogen is involved in damaging and degradation of pipeline steels under operation. The pipe can be hydrogenated from the inside and outside the pipe due to electrochemical corrosion. What's more, at hydrogen transportation, it can be also evolved due to molecular hydrogen dissociation, especially on the fresh surface formed under deformation, for example, under cyclic loading. So a long-term mutual effect of corrosion, hydrogen charging, and working stresses facilitates formation, evolution, and accumulation of damages in steel at the nano and micro scales. So hydrogen, on the one hand, accelerates in-service degradation of steels, facilitates formation of damages, and on the other hand, it facilitates initiation and propagation cracks in the damaged steel. Here you can see some examples of revealing of damage accumulation in pipeline steels by mechanical loading. And also it's visible crack branching due to delamination in pipeline steel under impact testing, and also opening of damages under tensile tension testing. Here presented data show mechanical properties of pipeline steels after operation and also in as-received state, and also residual hydrogen concentration. The main features of in-service degradation of pipeline steels are a significant decrease in plasticity, mainly in reduction in area, and also in brittle fracture resistance, impact strength, and fracture toughness. I'd like also to note that elongation in the degraded steel can be even higher than that of the delivered one. And this phenomenon can be explained by development of dissipated damaging in steel under operation, and then degraded steel become sensitive to cracking under tension, and elongation will symbolize real plastic deformation and also opening of these multi-cracks. And here we can see that operated 30-year steel is characterized by the highest value of elongation, and at the same time by the lowest value of fracture toughness and the highest value of residual hydrogen concentration. Current state of operated steel is usually assessed by changes in plasticity, strength, hardness, and impact strength, because these characteristics are mainly regulated by standards. However, based on many researches, strength and hardness and also elongation, as I was shown, aren't enough sensitive to in-service degradation of pipeline steels. So to correctly assess their degradation degree, it's important to choose informative indicators which are sensitive to degradation. And the most sensitive are fracture toughness and impact strength. Anisotropy of mechanical properties of rolled pipeline steels is a well-known phenomenon, and here you can see such a typical microstructure of a rolled pipeline steel. However, it's important to know whether long-term operation influence on this anisotropic mechanical behavior. And this research question was studied for two pipeline steels X52 strength grade after operation, and also in as delivered state and reference steel. Specimens were carved out in different orientation relative to the rolling direction of the pipe, and for a pipe elbow steel, the properties of the tension section were compared with the straight one, because it was suggested that degradation degree of the tension section can be higher based on revealed in bulk delamination in this section. So as it can be seen, the anisotropy in strength properties are insignificant for both studied steel. However, it's pronounced in the plasticity characteristic reduction in area. And also long-term operation influence on anisotropy. For example, for the low alloy steel, anisotropy in reduction in area was about 20% higher for the degraded steel compared with the as received one. Here presented data show sensitivity of pipeline steels to hydrogen embrittlement depending on their degradation degree and also orientation of the specimens cut out in different orientation relative to the rolling direction of the pipe. And hydrogen embrittlement susceptibility was estimated by changes in reduction in area due to preliminary hydrogen charging. So as we can see, the as-delivered state and also reference still aren't sensitive to hydrogen embrittlement at testing longitudinal specimens. However, they become sensitive to hydrogen embrittlement at testing transversal and especially short transversal specimens. And long-term operation influence on anisotropy in hydrogen embrittlement susceptibility. And we can see that the metal of the tension section pipe elbow was characterized by higher sensitivity to hydrogen embrittlement, especially at testing short transversal specimens, and also the similar tendency was observed for the low alloy steel. And here I presented fracture surfaces of specimens made of the tension section of a pipe elbow and tested without hydrogenation and after preliminary hydrogen charging. We can observe a ductile fracture mode for non-hydrogenated specimen and also features of embrittlement due to hydrogenated for specimens after hydrogen precharging. It's delaminating originated from non-metallic inclusions and propagating along the rolling direction, and also brittle transgranular cleavage. I'd like also to emphasize that hydrogen embrittlement susceptibility of the degraded steel is the highest when the fracture propagates along the rolling direction, indicated the weakest cohesion in this direction. So it's also maybe the main reason of development of in bulk delaminations in pipeline steels. And here are some concluding remarks. Summing up, anisotropy of pipeline steels increasing with long-term operation can influence on safe operation of pipelines, and obviously should be considered at assessment of possibility of usage of the existing gas natural transit networks for transportation hydrogen or its blends with natural gas. Thank you for your attention.